I thought I'd give you a fairly general talk today on the sort of things I do with microwaves because, as Steve said, I've been working for the last 20 odd years now, basically putting things in microwave fields and seeing what happens, basically. So it's a summary of all of that stuff. I'm a member of the High Centre of High Frequency Engineering as well, and so a lot of you know Paul Tasker, who originated this back it's been almost 20 years now, best part of 20 years anyway. And clearly there's opportunities for you to have a look around there later on if anyone's interested. So the talk really is in 4 bits, so I'm not going to say too much about the last bit because that's a talk in itself, but happily answer questions on it. But first of all, talk about microwaves, microwave resonators. I'm sure almost everybody in the room knows what a microwave is, but I am going to take it from basics and build up a little. And then look at these sorts of microwave resonant techniques for materials characterization, which has been my specialism over the time. But of course, if you can characterize a material, that material system normally makes part of a physical system, and then you can characterize that physical system, and hence these are very good sensors as well, because obviously at microwave frequencies, it's gigahertz, you've got lots of noughts to play with, so you have lots of resolution there when it comes to measuring changes. So again, excuse the basic nature of this slide, but it is important to get this out of the way really. Microwaves to me are between 1 and 100 gigahertz. Wavelengths then 30 centimetres down to about 0.3 centimetres. And that's the range we typically work in. In fact, we rarely stray about 10 gigahertz for the sort of stuff that we routinely do. And that microwave signal there you can think of as having an electric field, which is the red one, and the magnetic field, which is the blue one. And for a lot of applications, it's the red one, the electric field, that does the action, because that's the thing that polarizes a material, and hence is that polarization type interaction that we're studying a lot of the time. The magnetic bit is there, though. It's a necessary part, obviously, of the electromagnetic wave. And there are applications where we use the magnetic part as well. So the nice thing about microwaves is you do have electric and magnetic components. You put something in a travelling wave, then obviously both components excite the material. But the nice thing about resonators, as I'll explain, is that you have regions, nodes and antinodes of either field. So you can select which field does the excitation, depending on where you put the sample in the cavity. So I'll come back to that shortly. And the sort of things that we measure, anything we can really, but the main constitutive parameters that enter into Maxwell's equations, of course, are things like permittivity and permeability, which quantify the electric and magnetic response of a material. But the nice thing about this is that we're doing it contactlessly. We're just putting something in a microwave field, seeing how that field interacts with the stuff, and hence then working out what the stuff is doing from that fundamental interaction. Put conductivity down here because that's often folded in with permittivity, because conductivity is the response obviously due to an applied electric field. And these have real and imaginary parts, but what it means physically, of course, is that you've got a real bit which quantifies stored energy, and then an imaginary part which quantifies loss. So every time you polarize something, you store energy, but the response is also dissipative, so we can measure both parts of that, and hence get a lot of information about the system. I notice conductivity here I've written as a complex quantity because I've spent a lot of time looking at superconductors, and superconductors have a complex conductivity, or an imaginary conductivity, which makes them tick actually. So we're interested in measuring all those parameters as functions of frequency in the microwave spectrum, and also as functions of temperature. And microwaves, in common with all electromagnetic waves, of course, bounce off things when there's a mismatch in wave impedance. And to make a resonator, very simple really, you take a, yeah, you just have two microwave signals there. That could be an electric field, for example. Two microwaves traveling in opposite directions. Of course, you can set that nicely on a transmission line type resonator. Transmission line carries waves in one direction, discontinuity at the end, you get a standing wave, and you can design any resonator you want that way. You can have open circuit or short circuit boundary conditions at the ends. And this is a situation where you have an open circuit transmission line, okay, where you set up microwaves along it, and that's the standing wave that you get as a result of this microwave resonance. What you see there is the electric field and the magnetic field. You notice they're oscillating out of phase. So as soon as you set up this standing wave, instead of in the electromagnetic wave, the travelling wave, where the electric and magnetic fields are in phase. What we've now got are electric and magnetic fields which are 90 degree out of phase with each other. And as you run this little animation, you see that when the magnetic field, which is the blue one, is flatlined, and the electric field is maxima. And when the electric field flatlines, the magnetic field is a maxima. So what we've got there is the classical resonance where the energy is transferring from electric to magnetic and back again. A bit like a pendulum, pendulum, it's kinetic to potential to kinetic. And of course, if you introduce dissipation in that system, then that energy decays away, and then we end up with the concept of Q factor. So if we can measure the resonant frequency of this system, and also measure the Q factor of this system, then we can tell about the loss mechanism and also the stored energy mechanism as a result of the interaction with this particular field. The other thing to note about this is that you can see that the position of maximum magnetic field, the blue one, is in the middle, and the position of maximum electric field is at the ends. And that goes back to the point I said earlier, when you set up one of these microwave resonators, you have distinct regions where the electric field is big and the magnetic field is big, and they're not at the same point in space. So depending on where you put your stuff, if you want to try and measure something, you can excite it electrically or magnetically, or both actually. So of course this lends itself to the classical picture of acoustic resonance, where you have hotspots of the acoustic disturbance here. Of course those are half wavelength apart, and they'll be half wavelength apart if they're standing waves along a microwave structure. The classic example of which of course is a microwave oven. So we do work with Panasonic, who actually manufacture microwave ovens just north of Cardiff in the Pentwyn. So we have projects with them, and this is a console simulation from the Panasonic's microwave oven structures. That's the electric field distribution. So you can see the electric field hotspots there that do the heating of the food stuff. But what's thrown away a lot of the time is the magnetic field information, and the magnetic field has its own set of hotspots that tend to lie in between those electric field hotspots. So knowing this, we can obviously put the material in one of those hotspots and then excite it with either electric or magnetic field. So what are the sort of things that we're interested in doing then? So in all the time I've been working with microwaves, I think I've measured all phases of matter, all types of samples really, because if you've got a solid material and you want to know its property, then you can make a cavity out of that material. And a typical example there would be a piece of superconductor. So we've taken, for example, metals which go superconducting and make cavities out of them, and then cool them down, and then use the property of the resonant cavity to work out what the superconductor is doing. So the red stuff here is the solids. You can make resonators out of the thing that you want to measure. That's a little bit restricted because you have to be able to manufacture those cavities. You make them according to a certain size, and you can get them resonating then at any frequencies that you want. Samples are often flat, so you often have films. You can deposit thin films of samples, thick films of samples. And again, the red thing is the thing you're interested in. So there you can make a cavity out of a bog standard metal like copper or gold-plated brass, for example, or anything you want really. And then you can take your material of interest and then use that as an end wall replacement. And that again is a very nice way of characterising this red thing. But again, it's very restricted because the samples have to be flat. And you have to be able to match them up nicely. You can't have any gaps really in this because you lose a lot of the energy that you're preciously storing. So what we make a lot of use of is this basic cavity propagation technique, where we design a generic cavity called a host cavity, and then we put the sample we're interested in measuring or sensing inside the fields of that cavity. And that red dot there can be anything you want. It can be a crystal, it can be a powder, it can be liquid, it can be a gas, and we've measured all of those. And I'll give you some examples of these measurements as we move along. And the nice thing about this is it's often retrofitted. So, for example, you could have a liquid in a tube, as long as it's a plastic tube, by the way, and you can clip a microwave cavity around it and then work out what's going on with the liquid. It could be undergoing a chemical reaction. And a lot of the time, in chemical processing, you don't know for certain what liquid is inside the tube. You have a hunch it's ethanol or something, but you often need a secondary test to tell you what it is. So it's a very flexible technique that we've had a lot of mileage out of over the years. What I'm going to talk about mostly will concern this particular technique. So the challenge intellectually really is to try and design a microwave resonator or cavity or actuator around these materials of interest. And they could be anything really, from inert bits of material like superconductors through to the human body, which I'll come to towards the end of the talk. We're fortunate nowadays to have these boxes. If you pay enough money to Agm, they'll give you a nice microwave network analyzer. And what I've got here, this is a little microwave cavity I made for Merck, which is a big multinational chemical company. So they sponsor a number of our students in the pigments division to characterise what are transparent conducting oxide pigments, which they use in paints actually. And this little cavity here has a dielectric resonator in there. And for this particular application, you paint on a card the pigment that you're interested in, and you slot it into this as you would a credit card. And then this looks at microwave absorption in addition to microwave polarization, and hence they use this as a quality control mechanism now in the production of their pigments in Darmstadt. And what we see here is a nice classical frequency response to the resonance that these network analyzers give you. And you can measure that to an accuracy of about 10 Hz and about 10 gigahertz. So you have frequency resolution of the order of 1 in 10 to the 9, and hence you can measure very, very tiny changes in material. Properties. So you can track with exquisite accuracy, really, fundamental changes like chemical reactions, change in phase, anything of that nature. These are so-called main cavities that we make here. This is a cylindrical cavity, even though it looks like a rectangle. In there, there's a cylindrical space. This one, we basically insert samples into the hole. We can use that to actually excite materials with high power microwaves as well, or characterize with low power microwaves. And when we do the low power microwave characterization, then we are using microwave power levels around about a milliwatt or less. So there's no sense of heating, but the fundamental thing that we're measuring is heating, albeit at a very, very low level. I should say actually, the way we do the measurements is we just do a simple S-parameter measurement through the network analyzer. So we're mostly measuring an S21 parameter through the resonator there, which is what we're plotting here. And hence we use that then to work out what's going on inside the box, basically. Lots of resonant modes of these, so you can catalogue those modes. This is the cylindrical resonator. There's lots of TE and TM modes that some of you may remember from dim and distant electromag lectures. But all of those are quite interesting to us because all of them give you a different field configuration. So we normally design it. So this one is the one, this is the electric field excitation we use. It's the classical TM010 type resonance. But all these other ones are interesting to us because they just give you a separate mode of excitation. So we try and utilize as many of these resonant modes as possible. This one is designed here to go at 2.5 gigahertz simply because that's where microwave ovens work. And it's one of the allocated ISM frequencies. So again, these are the electromagnetic fields, the electric and the magnetic field in this TPEM 010 mode. And what you find is there's an electric field hotspot in the middle here, which is ripe then for putting materials into. So we often put a material along the axis of this and then use it to characterize the material electrically. The magnetic field in this mode is not so good for measuring the sample, but you can see that where the electric field is weak around the perimeter here, the magnetic field is actually large. So other modes give us alternatives of putting samples in regions where we can excite with magnetic field as well. This is the inside of that box. And we make it that way so we can pull it apart, put it back together again, nice and easily. You can see the little microwave coupling there, little coupling loop. Actually coupled into the microwave magnetic field for those who are interested in that. So this is what we physically measure. So again, going back to a bit of the physics really, in terms of what this measurement tells us. You know, it's nice to think of the empty cavity is producing a ping. We always think of acoustic resonators. I've brought a bell along with me just to illustrate this. But that's a nice high Q resonance. Okay, those ping, and the spectrum of that acoustically would look like that, albeit at lower frequencies. So that's a high Q resonance. The Q factor is basically the bandwidth or the frequency of that divided by the bandwidth. And the Q of these cavities, microwave cavities, tend to be of the order of 10,000 or something. They're high Q structures. Of course, if you damp this, then instead of hearing a ping, if I hold it, then it clunks rather than pings. And of course, the spectrum of clunk is something which also involves absorption. So if you look at the spectrum of a clunk, you see two things. One of them is that bandwidth broadens. The other thing is that the frequency shifts. It doesn't have to shift downwards, as I'll show you in a minute, but generally in these sort of acoustic resonances, then the frequency moves downwards. So what we're interested in doing, not acoustically, but using microwaves, is to look at the, first of all, the shifting resonant frequency, because that tells us about the redistribution of energy in the cavity. And then we're also interested in measuring the change in the Q factor, or equivalently the change in the resonant bandwidth, or the 3 dB bandwidth. That's linked to the power level as well, so that's not an independent piece of information. So that's what we measure. It's the change in frequency and the change in Q as a result of interacting the fields with a particular sample. And just to quantify that a little bit, I try to avoid equations as much as possible, but if you take a general sample and you put that into an electric field, and of course what happens physically is that that sample generates an electric dipole moment as a result of the interaction with the electric field. There's a charge displacement. What that does then is that that dipole moment has an in-phase and out-of-phase component. The in-phase component is linked to stored energy, but the natural dissipation in the system causes there to be a phase lag between the dipole moment and the applied electric field. And that's what gives us the dissipation then. So mathematically, if we know what the dipole moment is, and we know the applied electric field, U is the total stored energy here in the cavity. So if we know, first of all, the in-phase part of the dipole moment, that's linked to the frequency shift, so that's a stored energy term. The out-of-phase component, which is the imaginary part of this product, tells us about power loss, and that's linked then to this change in bandwidth. So this is classical cavity perturbation theory, where we link a fundamental property, material property, with changes in the resonant properties of the cavity. And of course, the idea here is for a very good sensor, for a given electric field, you want the dipole moment to be as large as possible. Now, sometimes that's a God-given thing. You have to just rely on the material having strong dipole nature, for example, water. But there are tricks you can do with geometry to ensure that that dipole moment is as big as possible to give you the biggest possible changes. And again, I'll come back to that towards the end of the lecture. So that's physically what's happening. Now, the nice thing about electromagnetism is you can often flip electric and magnetic fields and you get the same sort of expression. It's the same here, really, that if you put a sample in an applied magnetic field, then you get a screening current induced, or indeed a magnetization current if it's non-conducting. And that develops, instead of an electric dipole moment, you have a magnetic dipole moment. Then lo and behold, you end up with very similar expressions for the cavity perturbations. The in-phase part of n times h tells you about the frequency shift, and the out-of-phase part of n times h tells you about the bandwidth change. So again, you just need a simple theory linking the dipole moment to the applied field, and then you're able to quantify that dipole moment, and hence work out the fundamental properties of that material. So I'll start off giving an example of this, which is one of, it's fairly topical because it involves carbon nanotubes. I was going to do superconductivity, that's gone a bit old hat now until somebody discovers the room temperature, I guess. But graphite, obviously, graphene and carbon nanotubes have also been a hot topic really for the last decade or so now. These resonators are very simple. This is a hairpin resonator. In simple terms, it's just a bent U-shaped piece of copper. But of course, that's a parallel plate transmission line with a short circuit down that end and an open circuit up at that end. So that sets up a standing wave along it. And the fundamental resonance then is simply, it's a bit like an organ pipe calculation where you set the length equal to a quarter wavelength, and you choose a length of 23 millimeters, and lo and behold, it goes at 3 gigahertz. It's as simple as that. It's actually 25 millimeters really, but there's an end effect, you see, which messes it up a little bit. But anyway, the electric field, the magnetic field in that structure is big down here because that's where the short circuit is. So there's a nice region of maximum magnetic field there that threads through between the plates when it resonates that you can use to excite the material magnetically. And then there's an electric field distribution that looks like that, which is large at this capacitor type end, where it's an open circuit. So again, if you have a sample in a tube, you put it into that position, it's magnetic excitation. You put it into that position, it's electric field excitation. And this is what you end up with. You get different types of behaviour here. This shows you what happens when you introduce, for example, a little metal ball into the electric field. This is the empty cavity response. So what you find is that when you put the ball into this electric field region, and it's metallic, you end up with a strong reduction in frequency, because nothing produces a larger electric dipole moment than a metal, because the internal field is reduced completely to zero, or almost to zero anyway. If you put that metal into the magnetic field region, however, then you notice that the frequency actually increases. And that's simply a result of the reduced flux linkage in this region. If you reduce the flux linkage, you reduce the inductance, and that pushes the frequency up. So you can get different quantitative types of behaviour here, depending on the conductivity of the material. For example, dielectric materials will always give you a reduction in frequency, but metallic or conducting materials will actually give you a frequency increase if you put them in a magnetic field region. You also note there's an extra dissipation here. You notice the peak power is different, the bandwidth is larger here, and that's simply because when you place a material in a magnetic field, you're inducing currents in it, and those currents dissipate. So you have any current dissipation, which you're measuring in this context. So that's what tells you what we use this to calibrate the systems, because if you know the size of this ball, you can then basically use it to calibrate basically work out the scaling factor between the dipole moment and the changes that we're interested in. So go back to carbon nanotubes then, just to put some context into this. You're familiar with the various allotropes of carbon here. The thing about carbon nanotubes is that they are, if they're conducting, they're ballistically conducting, and people have proven that by contacting to them. But the nice thing about these microwave measurements is that they don't need contact. You can just basically put the material into microwave fields. So what we've done measurements on carbon nanotubes. And carbon nanotubes, of course, are just rolled graphene sheets, and they have diameters around about a nanometer. And this is what happens when you try and do measurements on graphite. Graphite is a conductor. The conductivity is about 10 to 4 times less than that of copper. But if you put a graphite powder inside one of these cavities and you excite it with a magnetic field, you get something like this. This is the cavity without the graphite, and this is the cavity with the graphite. And you see that there's actually no change in resonant frequency there. There's no sense of any skin depth being induced in the graphite sample, simply because the conductivity isn't large enough. So what we find is that the magnetic field enters the graphite, completely penetrates it, and there's no concept of skin depth. There's dissipation, however, because the graphite tries to screen the magnetic field by inducing an eddy current, and there'll be dissipation as a result of that due to the finite conductivity, but there is no frequency shift. If you do the same measurements on conducting carbon nanotubes, then you get a very remarkable result, really. Well, at least what I'm first thinking about it, is that you end up with a frequency increase as a result of the material going into this magnetic field region. And that is a classic example of conductivity being large enough so that you basically see the effect of skin depth. You're screening the magnetic field from inside the sample because the conductivity is so large, and that's causing this increased frequency due to a decreased inductance. And that's what we see in carbon nanotubes. But if you think about it, a carbon nanotube has a conductivity, a sheet resistance low enough to allow the magnetic field to be screened from inside of it. And that in itself, you see, is quite a remarkable result. Now, if you do some simple analysis of this, then you end up with two bits of information. You can take this frequency shift, and then you can work out exactly how big or how little should the sheet resistance of the carbon nanotube be to exhibit this type of behaviour. The other thing you note is that there's a massive broadening of the bandwidth here. And you think, well, hang on, if they're screening, how can you get such a large dissipation if the conductivity is so high, if the sheet resistance is so low? And there's a very simple answer to that, is if you could pulverize these nanotubes flat, so that they covered just a plain area, then I think it works out that 1 milligram covers 22 square metres. It's that's how much area there is to them. So you get a massive broadening of the barrier, not because the sheet resistance is high, but because the sheet resistance is so low that the area is massive. And that's the thing that's giving you the broadening. So if you can take two parameters here. One is the shifting frequency, use that to work out the sheet resistance. Take the broadening of the bandwidth, use that to work out the sheet resistance. And both of those results point to sheet resistances of the order of 10 to the minus 5 of an ohm. So what we're concluding here, which people know anyway, is that these carbon nanotubes, when conducting, are basically ballistic conductors. Their sheet resistances are unimaginably small. They're not superconducting, they're not perfectly conducting, but they're as conducting as anything that we've got, basically, as a result of these tiny, tiny sheet resistances. So that gives you an idea of the sort of fundamental studies that we can undertake with these methods. I want to talk about applications now because I need to move on to the second part of the talk. These are the resonant traces that we get when we put liquids into one of these cavities. This is an electric field hotspot, so we're putting liquids in tubes, exciting them with an electric field around about 2.4-ish gigahertz. And you notice here, you have the empty cavity over here, and then you get different signatures for different liquids, and that's simply because different liquids have different permittivity values. These polar liquids, which are often used in medical and biosciences, are also highly polar, because they're used as solvents. And that means that their permittivities are also very, very highly frequency dependent. So what we've got here is some fingerprinting starting with different liquids. So you can see that we can distinguish very nicely at one frequency between various liquids, not just by measuring their shifting frequency when they enter the cavity, but also by measuring their broadening of bandwidth. The nice thing about this is that this is all happening at one frequency, but if we try another mode, different frequency, we get a different set of curves, and hence what we're doing there is we're looking at broadband dielectric spectroscopy, basically. By looking at different resonant modes, we can then use that to distinguish very carefully between these different types of liquids, indeed different liquid mixtures as well. This is what happens, for example, when we take two liquids of quite massively different polarities actually. Acetonitrile, which is a common solvent, and toluene, which is just something which is less polar, which happens to be soluble within acetonitrile. And this is what happens when you go from 0% acetonitrile to 100% acetonitrile. And you notice that you can use this to actually measure the composition of two phases, 3 or 4 phases even, but then it becomes a somewhat more complicated problem. You notice there's a continuous variation of frequency shift here as you go from 0% one phase to 100% the other phase. You also notice there's a dip in this, which I can't explain, but maybe I'll leave that one until the end. Okay? But you can use this clearly as a detector. In this case, for example, of a system that involves acetonitrile in toluene. So it could be looking for water in the materials as another thing. You know, it's very sensitive to water, this. Water being a massive absorber of microwaves at these frequencies. So these sorts of applications then, where does this put those microwaves as a potential sensing technology? Well, this is a very generic graph that lists the sort of competitive technologies we have to microwaves for measuring systems. We've got mass spectrometry, NMR, EPR, and other things here, impedance spectroscopy, for example. And the microwave response that we measure tends to be on the sort of intermolecular level most of the time. It doesn't really take us down to the atomic, and it's not really on the macroscopic length scale. So we're pretty much fixed by that, really. It's all about interactions mostly between molecules when it comes to sensing applications. And then the amount of information that we actually measure is not very much, really, because at each resonant frequency, we're only measuring frequency shift and bandwidth change. So there's not a lot of information there. So the information content is quite low. So that pictures microwaves down here. And of course, you've got these lovely fingerprinting type techniques like NMR, for example. Raman is another example, where you can really pick out, materials in very, very small quantities. But the nice thing about the microwave technique is that it's immensely sensitive. Because it's a resonant technique working off a high Q resonator, and we're working at gigahertz frequencies, so we can measure very small changes in frequency. The sensitivity is huge. The other thing, however, is that we can sample very quickly as well. So we push these measurements at sample rates of up to about, well, we can do 10 kilohertz very easily. There's nothing in principle that's pushing it even faster than that. So we can collect information incredibly quickly as well. So although there's not much to measure, we have sensitivity and we can do things very rapidly, which then breaks microwaves away from these other techniques, which are inherently quite slow and also suffer from the lack of sensitivity. We find it to be per unit sample volume. This is an example of a reaction occurring in real time. So this is an esterification reaction where these materials are being converted into this ester. That esterification chucks out water. So anything that chucks out water should be a good signature, should give us a good signature for microwaves. So what we're doing here is measuring the Q factor of the resonator as that chemical reaction occurs, and the generation of water here is pulling down the Q factor. It's completely non-invasive. This is happening in a tube inside a resonant cavity. So you know, there's no sense of it. It's just microwaves are just tickling it really. I'm not doing anything other than that. This is another example of curing resins. This is UV curing of resin. So this is a resin foam, different compositions here. What we're doing is we're switching UV on here, and then we're looking at the dielectric property change of the subsequent polymerization process of the resin. So what you can see here, you can see this is over a period of about a minute or so, but the collection of data here can be as fast as you want. So we can actually look at the dynamic of curing, and that's quite interesting from a polymer science point of view. But from a practical point of view, you have a non-invasive method of determining when something is cured. Again, it's simply because the microwaves sit in the background and interact with the material, and hence it's completely non-invasive from that perspective. This is another type of resin. It's a very simple resonator based on a coaxial cable actually. So we can take a commercial coaxial cable like this, make it a certain length, chop its ends off so it's an open circuit resonator. So at the end we have a strong electric field, and then we can dip that into anything we want and then get some dielectric property measurement of the thing that it's dipped in. So this is an ideal sensor really, is a T-piecing in a stainless steel tubing type system. What we end up with here are many modes. If you make the resonator long, you get greater density of these modes because the resonant frequency is inversely proportional to length. So this one, for example, is 30 centimeters long, and that gives a fundamental frequency curve around about 350 megahertz. Then you've also got 700, 1050, 1400, and so on. This is what happens. The red curve there is when the resonator is just sitting in air. And the blue curve is what we get when the resonator is dipped into a liquid. So you can measure the dielectric property of that liquid at all these different frequencies, and hence you open up the dielectric spectrum then of that liquid, which again allows you to have nice fingerprinting of that particular liquid. And this is how we can embed this into a microfluidic circuit. So what we've got here are these circuits where we can machine these little ducts in there, and then the resonator interrogates this region here, which could be part of a much more complex microfluidic circuit. And this is the sort of fingerprinting that we get then. This is plotted as a function of frequency, so it's taking the data that we generate from this type of resonator. This is the real permittivity, imaginary permittivity of various solvents measured in the few gigahertz region, where there's quite a lot of change in these simply because of they're classified as biliquids. So this is where the molecular rotations are happening. This is the time scale for those relaxations and rotations. I should say actually, this particular sensor we're currently working on at the University of Sheffield, and we're using it to try and quantify the amount of hydration there is in particular tissues. So the guy I'm working with up there actually is an expert on premature birth, and we're trying to use this as a means of trying to examine the role of hydration of tissue, specifically that of the cervix, in the predictor of early birth. So it's quite early stage yet, but it's giving some quite nice results because we're measuring basically water content, and consequently anything involving microwaves is very, very good at that. This is some work of my PhD who's Ali, was somewhere here, I think. So Ali's developed a microfluidic sensor. This is a split ring resonator that has two active regions in there. There's an electric field. And this is a liquid passing through capillary through that system. And this is a segmented flow. So what we've got here, oil packets and water packets. And this is just monitoring very rapidly the resonant frequency over time as these little fluid packets shoot through the resonant system. So what we've got here is a state there, which is basically when it's completely oil-filled, and a state down here when it's completely water-filled, and then intermediate states when one is filled with oil and one is still filled with water. And we can use the dynamics of that to compute A, what the liquids are through its permittivity value, and then B, the dynamics of the flow in terms of the velocity of the flow and actually the length of these packets as well, these segments. So you can compute an awful lot of this from the dynamic that we measured. And this is just simply measuring, actually there's two things here. One of them is resonant frequency, which is the black trace, and then the red one is basically the microwave loss, which is listed here just the peak power level. So that shows you how you can extend this to microfluidic circuits. I'll finish off on this application, which is another medical application that we're working on. In fact, Hunjay is my postdoc working on this with me, and this is using microwaves to try and measure blood glucose. Obviously, diabetes is a huge problem for world health at the moment. It's going to grow worse as well as diets are not improving, basically. And the prediction is already more than 6% of the world's population are diabetic, either type 1 or type 2, which is obviously the one that's brought on by poor diet. And the issue with diabetes really is poor management, which can obviously lead to massive personal health problems and associated huge health costs. So anything that tries to encourage the better management of diabetes is a good thing. And one of the problems is when you do research on this is that you do have to prick your finger continuously. And those of you who are diabetic know how bad this can be. Like we don't have any fingers left actually because we prick our fingers so often in doing these types of measurements. So what we're trying to develop here is a sensor that will tell us about blood glucose without the need for extracting blood. So we can quantify glucose in solution. This is glucose in water. Same thing happens in biological type solutions like PBS, for example. If you add glucose to water, two things happen. One of them is you suppress the polarization of the water, and the other thing is that you increase the loss. So there are signatures of glucose within aqueous solution. And what we're trying to do is trying to look at those signatures through microwave resonators that we attach to the body. What we've designed is, this is our vision for the system. It's actually wired up at the moment, but what we hope to do is to develop a little microwave sensor like that that sits on the body, onto which we attach the appropriate medical electronics, and in there will be a transmitter that transmits to a data logger, and hence we measure non-invasively the blood glucose content in blood using these microwave resonator techniques. I should say that this is probably the hardest problem that we're trying to tackle using this type of technology, and it's fraught with difficulty. One of which is, of course, is how specific is this to glucose, which is a very good question. And all I can say up to this point is that we haven't really found too many interference other than glucose at this point. And this is what we measure. So we have our Cardiff sensor here, which is the blue one. This is our inferred blood glucose measurement over a period of time. This is a blood strip measurement with the same parameter, and this is the best continuous meter that you can buy currently, which is this red one here. And you notice the red one isn't too good because A, the signal is washed out quite a lot, and the other one, it's delayed as well because the continuous glucose meter doesn't sit in blood. You shoot it into your torso and it actually sits in interstitial fluid, and the uptake of glucose in that is different to that in blood. So what we think we're measuring is mostly blood, and we get pretty good correlations between what we measure and what we get for the invasive method that involves either glucose analyzer or the conventional blood strip meters. But it doesn't always work. Okay, sometimes it does, sometimes it doesn't. It's location sensitive. So we haven't really cracked this problem yet, but we are getting encouraging results. And we did just finish a clinical trial yesterday which again is just reinforcing our data center. So the next step in this is trying to make it wireless, which I think is an easier question than actually making it work in the first instance. And what we need to do, of course, is to reduce the cost here, reduce the instrument size massively, and that again will allow microwaves, not just in the blood glucose application, to break away from these alternative technologies. I'm going to have to stop here, I think, because I have reached my end point. I haven't talked about microwave heating in any way. There's a summary slide here which I can go through, but if anybody's interested, I can email this talk to you, and then you can have a look at it in your own time, basically. So I should say that we are also working with microwave heating applications. We're working in pharmacy at the moment, for example, using microwaves to try and extract DNA out of various pathogenic bacteria. Dr. Tina Joshi here is an expert on that, so together we're trying to develop a point-of-care detector of bacteria that will allow us to tell us what bacteria is there within 5 minutes or less, we hope. So instead of sending a sample off to the lab, if you've got C. diff infection, you want to know within 5 minutes. You don't want to know within 2 days, really, for obvious reasons. So these are the sorts of things that we're doing with microwaves. I hope it's been illustrated anyway, interesting. There's lots of people I can thank as well. Lots I've left off the list, I'm sure. So I'm going to stop there. That's my allocated 45 minutes. So thank you very much.
Thank you.
Let's take a few questions.
Yes, absolutely.
Well, while you're thinking, I've got a quick one.
Yeah.
The glucose monitor you're referring to.
Yeah.
Can you give any kind of idea, assuming you manage to solve these
Yeah.
problems? Let's say you've got something that works, you've cracked the sort of slightly variable results. How long might it take before one gets something like that, such as in general usage? Because it's got to go through lots of sort of approval. How long does that process take?
Oh, well, I think it's going to take a few years yet. Difficult to estimate, but because it's only giving you a reading, it depends what you're using that reading to do. So if you hook it up to an insulin pump, for example, where you could basically kill somebody if the reading is wrong, then that's a different ballpark to just having a meter that gives you an indication of your blood glucose level. If it's kept as simply a piece of information that is sent to the user, then there's no reason why this couldn't be on the market in 3 years. But if it was hooked up to an insulin pump, then it's more like 10 years or more, because of the different levels of FDA approval.
Okay, thank you very much.
Very interesting presentation. With over 400 million potential type 2 diabetes patients ahead of you, it sounds to me like there should be a potential to get good funding to be able to improve the non-invasive diagnostics technique. So is there a way of improving that non-invasive technique?
Well, there are people who try to use the microwave before, and there are other techniques which, for example, use infrared, and nothing has ever come to market which is non-invasive. But the nearest you have are things which probably involve microneedles, which are minimally invasive, still involve the extraction of fluid, basically, interstitial fluid or whatever. But there's nothing out there which is truly non-invasive, but there's been a lot of money pumped into various startup companies. The one, what's the Glucotrack is the one that's closest to market. That's probably had about $20 million of investment up to this point. We've had nothing like that, by the way, so we're somewhere off. It would be very nice. They're not insurmountable problems, basically.
Sounds to me like you've presented a good business case as well as a technical.
Yes. Yes. Well, we got nice product funding from the Wellcome Trust currently for their translation award, which hopefully will allow us to go through to the middle of next year, and then beyond that, then we need to secure more funding. But at the moment, it's very definitely a university project that is still at the sort of sensor front end, really, rather than developing a commercial product. It's knowing when to let this go as well. I'm an academic, and I think I'll stay an academic, really. But the potential for improving people's lives is enormous. It's a good use of microwaves.
Okay, well, once again, thank you very much. Please accept this small gift
Oh,
from
thank
us.
you very much.
It's a combination of bar and memory stick.
Oh, brilliant.
Thank you very much. Thank you. One last thing I'd like to say before those who are leaving and not attending the ExCom meeting, and that is that Tarek Durrani here is petitioning for president of the IEEE 2015, and he needs to get